All right, so, okay, so this is sort of like the motivation for, it also was my motivation for the next part of the talk, but it's, at least for the first part, is going to be fairly independent of everything I've said. It's just, the important bit is just to remember that in those sort of applications, there are a lot of things we don't know, and we have sometimes no chance to learn the parameters, or for sure not the computational power to do so. And so, I mean, what can we do? What can we do with this? And if we still believe we should do something Bayesian, and so that's well, the idea actually comes from quite a while ago. People have tried to develop some sort of alternatives way to like represent uncertainty and things that maybe not random, but more what people call the epistemic uncertainty is just, well, you don't know something, but you're not saying it's random, and that makes a difference. But I've really developed, so most people, they don't really mix this with Bayesian inference. They try to do something with it. Sometimes it's quite complicated, but I wanted something simple and that can sort of address the sort of problems we have in target tracking. So, all right. So starting really from the beginning, let's reset all the notations. Some of the notation are reused, but it's, I mean, are in common, but they don't mean the same thing. It's just reset all notations. So what's the motivation? So the idea is to use alpha measures. And so an alpha measure is actually is used in measure theory to, for instance, to define a Lebesgue measure. But basically, you can just see it as some sort of upper bound for probability measures. So, and as I say outer probability measures because, as I'll explain, I want them to basically give mass 1 to the whole space, so they to have, I mean, they need to have this property. So if we start with something standard, and we just introduce a random variable, and we have some conditional probability distribution for it, depending on some parameter theta. But for instance, we know absolutely nothing about theta, right? Well, what can you do in that case? And I mean, for instance, this big theta space, maybe it's R, maybe it's RD, but if you have no idea even on bounds on theta or something like this, you can't use uniform distribution or something like this. You want something that's weaker than this. You want to say, I really know nothing about it. And so, well, the first thing you can do is, well, the probability for X to be in some subset B, you can say, well, at least it's less than the probability for X to be in B, given theta, and we take the maximum over the supremum over O theta. So this is sort of a worst case approach, and that's going to be true. And this, for instance, is an outer probability measure. So so the difference between probability measures and outer probability measures is that well, they satisfy the same set of conditions, except that this guy or this guy probability measures, they're additive. If you have two subsets that are disjoint and you can evaluate, you say the probability of the union is the sum of the probabilities, right? That's what probabilities does. And so an outer probability measure, it's subadditive. So all the time, for any subsets, this guy, if you look at it as a single term, the sort of mass it gives to B union B prime is less than the maximum between the mass it gives to B and the mass it gives to B prime. So anyway, so for instance, starting from here, this is not very useful because, okay, we've said something, but we're not going very far with this. So for instance, we can say, well, let's say in this case, at least I know something about theta. Maybe it's some subset A. So A might still not be finite or compact. So this is still different from saying there's a uniform distribution over A, because it might not be even defined, right? Depending on the sort of space you're looking at. And okay, that's a little bit more useful. Maybe if you, some people try to do this sort of interval analysis, and you can sort of see it this way, saying, well, we don't know anything about theta except it's within A. And But to have a bit more flexibility, what I consider is I just replace this indicator by some function, and this function doesn't need to have a lot of properties. It's just it's a non-negative function, and it has to have supremum 1. And this thing is really just for intuition. We sort of forget about it, and now we define p bar. So in this talk, all p bars are going to be, even with some indices, are going to be outer probability measures. And I say, well, that's how I define, let's say, this outer probability measures. And I can verify this gives 0 to the empty set, 1 to the total space, and it's subadditive. So it works. That's an outer probability measure. So what's nice is at least if you accept that you can treat this part of the expression as in a sort of Bayesian way. If you accept, you can, for instance, write Bayes rule with this guy, right? Why not? I mean, let's look at it. Then you actually realize that this part that I'll call possibility function, it actually verifies the same sort of rules as usual, but we replace integrals by supremums. So this is marginalization. Let's say now that big theta is a product space. If I want to marginalize over the second component, instead of integrating, just take the supremum. You can sort of show this using this sort of expression. And again, as taking it as an assumption that Bayes rule not for this one, but here you make an assumption that Bayes rule makes sense, and you can find that the sort of posterior possibility function given theta 2 takes this form. So here again, basically with Bayes rule, but with a supremum here at the denominator. I mean, if you rewrite this. Yes?
So you say assume this, then that. So does this hold for any conditional probability distribution? But what if, like, x0 for the data with which x is generated?
Sorry, the last part?
So say x is generated according to distribution parameterized by theta.
Oh, so okay, so that's what I meant when I put in gray. This bit is sort of the motivation.
Okay.
So and then it's especially if you start to divide, then I mean you would need a lower bound, right? So this is really just the motivation. But then we just focus on this and we say, what if we treat this? If we basically try to do inference with this rather than with probabilities, right? I mean, like, you say well, it's a funny idea, but I mean, let's check, right? Why not? So, well, there's some nice consequences that here you don't need a reference measure. So actually, even that theta is discrete or continuous is just the same. You can evaluate it pointwise. This possibility function pointwise, and so in particular, you just need to make sure that the supremum is 1. So you can sort of recycle your standard probability distributions. So uniform distribution now is just the indicator. There's no normalization because we don't care about the size of AB. In particular, AB could be the whole real line and be the same. And that's really just saying, for instance, we know absolutely nothing. If AB is the whole real line, we're saying we know absolutely nothing about X, about what's going to happen here. So I'll be a bit more precise later. So we can recycle our Gaussian distribution. We'll see that's very useful. So it's quite nice because you sort of drop this the normalization here. Same for students T, same for Cauchy. Actually, most distribution on R that I've tried, they actually take very nice form because satisfying supremum equal 1 is a lot easier than satisfying integral equal 1. And actually, you can take this and make the 2 here any power you want. It's still true, right? So you have a lot of flexibility in the sort of shape of those possibility functions. And for instance, I mean, here we drop this fairly nasty stuff. So that's nice. Also, what's nice, I think, if we think in terms of Gaussian, I'll do a lot in the talk, is often is really, we want to, for instance, truncate our Gaussian. We say, okay, I want to assume Gaussian, but I don't want the tail. I know there's some bounds. If you do this with a probability distribution, you need to renormalize, and usually this renormalization is not going to happen. It's not going to go very well if you want try to do any operation. But here you can just truncate as long as the mode mu is within your interval, and that's still a possibility function. You don't need to do anything to it. It still has maximum 1. So as I was saying, we can introduce also a lot of new functions. I mean, because it's very easy. And so one problem here, is that usually distributions on the integers, actually, they don't translate very well. Because, for instance, the modes is not actually on the set of integers or something like this. So then you have then the expression is not nice. So you could say, okay, that's a big problem. But actually, all those expressions, if we take, for instance, here, if we take mu integer, and we consider actually here the set of integers, then we have Gaussian on the integers because we just need maximum 1. So you can do almost anything you want as long as you retain the mode in your set, and you don't need to renormalize or anything. So that doesn't say much. It's like, okay, well, why not? But it doesn't make things more complicated, at least in that sense. So, but all this, we're like, okay, but we lost everything. We don't have random variables. We don't have anything. How can we say anything sort of in a more rigorous way? So we can sort of extend random variables in a fairly intuitive way. I mean, this is nothing smart. It's just to say we can sort of build the right tools. And so I call them uncertain variables because they're not random variables. Could keep the same name, that would be unclear. So, but this time, basically, we on top of the sort of usual probability space we have another sample space that is just gives you the state of things you're not sure about. So it doesn't need any structure. It's just saying, for instance, I mean, if your problem is the position of the pointer, you say the pointer can be anywhere on the screen, right? But maybe I don't know if I close my eyes, I don't know where's the pointer. Then the whole screen is your sample space. It's all the possible, for instance, position of the pointer. I mean, it works exactly like omega r, but there's nothing random there. So, and we can, to get the constructions before, basically, we can add to this proper probability space that depends on the omega u in omega u. So in the big omega u. So because maybe some of the random phenomena they depend on things that I don't know. So if someone has a box of dice that are biased in different ways and decide to pick one, but I don't know which one, right? And then throws it. There's an uncertain part and the random part, right? You could argue. I mean, maybe the guy is picking on purpose one of the dice, but you just don't know, right? There's no randomness in there. You could claim you can model it if you think it's random. You can model it as random, but that's one example. So we have state space, parameter space. It's quite so basically anything we're not sure about is going to go there, and everything that's random is going to go there. And so then we can basically just mimic the random variables, but on this sort of product form. So in particular here, there's no dependency. It's completely separable. And so this guy is a random variable. And basically, what this thing is saying here, you don't need to think too hard about it. It just says that this mapping, basically, from omega u to my parameter theta is informative enough about the randomness in XR that this conditional distribution makes sense. If without this assumption, basically, you can't write this because so in the example I gave, if you give a theta that says I don't know the position or the temperature outside, and you want to deduce what's going to be the outcome of the dice, there's nothing you can do, right? That's not well defined. So it's really nothing smart. It's just saying it's sort of related to measurability, but here where there's no measurable space, we're saying this mapping here is informative enough, and it's quite intuitive, I think. So just to simplify things, I'm actually going to kill everything that's random, but we could keep on keeping both random and uncertain part, and we would be okay, except the equations would be a bit more complicated. So I kill the random part and I assume my parameter space and state space is just the same. So basically, I just work with the possibility functions. And well, one very useful concept in probabilities is an independence, right? So so here it's nothing smart. We just say those uncertain variables, they're weakly independent. In this case, and in this sort of fully deterministic case, they're weakly independent simply if the possibility function factorizes. So the nice thing with those possibility functions also is that we can, for instance, if I want to simplify my representation, so they're not, in a sense, they're not unique. If you have a joint like this, that's not weakly independent, let's say, here, and this guy is not weakly independent, it doesn't separate. But for instance, I take the marginal over x, and now I claim that actually I know nothing about y. This is still a valid representation. So I've lost information. If I do this, one way or the other, I say marginalize, and I say I don't know anything about the other variable. I've lost information, but if this makes my life simpler, maybe for later, that's still valid. I've just decided, I've just decided to lose information. So basically anything that's above, like if you take any functions that's lower bounded by a possibility function, that's still a valid description of your uncertain variable.
What do you mean valid? Do you just mean that it is a possibility function? Or
Yes, of course, it's still a possibility function. What I mean is really in this context. So in this context here, x, basically, if you given omega u, p is unique, right? If you're given xr, you know p. There's only one probability for one random variable, at least in this way, right? But here, for uncertainty, there's no one possibility function. Maybe I know the value of this thing. It's going to be like indicator of 1 point, 1 theta. Maybe I have no idea, so it's going to be 1 everywhere. So basically, as long as we're not claiming we know more than before just by doing some arbitrary operations, if we decide to lose information, that's fair, right? We can do this. It's basically we're forgetting some information if that's convenient for us. So this is just to say so this is in general, of course, for some specific families we can be a bit more precise than this. But even if we know that things are related, we can forget this relation and sort of make them independent again, like this, weakly independent. So I think it's interesting to look also at expectation. Because if you don't have the notion of expectation, you're not going to go very far with, if you want to do inference, for instance. So, and the sort of most direct way, I just copy, again, not being smart, I just copy everything that's probabilistic. And so here, that's just a uniform norm, right? So I'm just saying supremum of phi x fx, right? So, for instance, but in this case, it has to make sense. You have to take phi non-negative. So you're like, well, that's and it has to be a function, and by function I mean something on that real valued mapping. So that's very, of course, it's non-negative. Sorry, it's non-negative. It has to be real. So this is very restrictive, and you say, well, maybe it's not very useful. I mean, what does that mean at all, right? But at least in some cases, can be useful. So, for instance, if we think in terms of information, by following the same step as introducing the self-information in probabilities, we can introduce something similar for here, just minus log of this possibility function. And using this definition of expectation, then the entropy is just this, is quite obviously, right? And so this it's sort of similar to the definition of the entropy in probabilities. But for instance, one thing that's nice here is, it's meaningful both on countable and uncountable spaces. In uncountable spaces, you want to define entropy is hard. And people define differential entropy, but it's not always positive, and it's a problem, actually. Almost everywhere where it's a problem to go from countable to uncountable in probabilities, we don't have the same problem with possibility functions. And actually, this you can also interpret it, also makes sense intuitively, because this self-information is also called the surpriso. So basically, if you say if f de x is 1, then you're not, and you're given x, maybe x is for instance, you're given x is a true value, then you say, well, I'm not surprised by this value. I was because I took the f of x equal 1. I said the value x is completely possible. So this is actually makes complete sense, and this is sort of a maximal surprise also. How much do you expect to be surprised, in a sense? So you can still make sense out of it. Yes.
So it's infinity somehow with respect to distribution on x? Or
No. Here there's no distribution. Here is just the actual supremum of this.
which only depends on the possibility function.
Yes. Yeah. Only
There's
depends
no
on.
distribution of
No. There's no distributions here.
This is just a function of the possibility function that has nothing to do with x.
I mean, so here. Sorry. So here I collapse everything. I say there's no randomness. So it's just to make random theta prime, and so it's just to make things simple. I collapse everything. So now only interested in like basically an uncertain variable. There's no random part. It's just something I don't know, but I don't model it as something random. Right? So okay, but the more intuitively appealing thing is actually to take the argmax, to say that's what I expect if I say. I mean, if f is Gaussian, for instance, and you have to make a bet, you say, well, I'll take the mode, right? So that's the sort of more intuitive things to do. And of course, if you do maximum likelihood, then I mean, it makes perfect sense, right? Then you this is your estimate, right? So this doesn't mean much, but and also it's nice you can do like profile likelihood is super easy to justify because you take the supremum of the likelihood. So it's just like remarks, right? Oh, so yes. So in generality, you can allow this to be set value if you want to. So right. But yes. For simplicity, you can think as a unique maximum. And so, well, you could say, well, this is just comes out of nowhere, right? But if you try to write a law of large numbers, so if you have a collection of just weakly independent and certain variables. So I mean, you can think of it as the standard law of large number. Then you can write the possibility function of the sum. So I mean, just takes this form. It's not very complicated to derive, and so under some weak conditions, actually this one I just made it for simplicity. You can also have set valued here. You can show that if you take the limit, this becomes the indicator of the argmax. So that actually confirms completely this approach. So I have to say it's more difficult to interpret like in practical terms, but I think it's interesting to see that. And of course, you can also do a sort of CLT. So the CLT is a bit more complicated, but just to, I mean, I could have made it a bit simpler, but here I just assume dimension 1 and there's a unique maximizer. And so, and let's say our function is twice differentiable on the right of mu, so on mu to infinity. And so this time, rather than looking at Sn, of course, I do a CLT, so I look at square root of n Sn minus mu. And on purpose, I don't normalize by any sigma or anything, because actually, what is sigma, right? Where is the standard deviation with the variance? You don't know. And actually, the point of this CLT is to tell you what is sigma here, what you should use. So you do this, and you find, so basically, if it's 2, if the right derivative, the first derivative is non-zero, so it's actually quite picky around mu, then you just have indicator again. But if the first derivative is 0 and the second is non-zero, you get Gaussian. That's pretty nice. And you get Gaussian with what? With standard deviation minus 1 over f prime. F second, sorry. So in this case, I just assume the right and left are correct. And so now this law of large number and the CRC, what they give you exactly the Laplace approximation. That's just Laplace approximation. You take the mode and you take the second derivative of the function of your probability density function at the mode, and you take the Gaussian that corresponds to that. And so these things actually they match exactly with the Laplace approximation. I think that's interesting. So, but again, you could say, well, that's I mean, it's maybe not very natural and it's very built up, but okay, let's do something a bit more. So Markov chain is very easy, and it's just the same thing. I mean, we have weak instead of normal independence, but it's the same thing, right? Actually, I'm going to skip this. It's not important. So okay, let's try to do some inference now because that was the point. So I'll say be able to do Bayesian inference with something that's not as basically something that's a bit more relaxed than probability densities. So since I've defined, and you see why I defined my uncertain variables, I can write something very standard like this, except everything is just uncertain variables. So I have some noise, but this noise, again, is not random. It could be anything. It's just some perturbation I don't know. If you think of someone who's walking around, you're going to have a hard time to justify it as random, right? But we just don't know where the decision, we don't know where the guy is going, we don't know what decisions he makes. And so that's sort of the noise that's going, for instance, if we say this model is going straight line, sometimes it's going to change direction, but we just don't know when and we don't know how much. And so that's what this thing models. Observation is exactly the same thing. Right? So all this is cool, but now we can write, since I said before, we have marginalization, we assume Bayes rule. So we have, that's filtering equations, right? That's the one you get. It really looks like a standard Chapman-Kolmogorov equation, but you have supremum instead of integral. Here it looks like standard Bayes rule. Again, we just have a supremum instead of integral here. So so actually this supremum also makes a difference because, but I think the important bit is here. So, and normally in Bayes rule, at least on uncountable spaces, actually you're hiding a Radon-Nikodym derivative because, I mean, if you condition on observation, a point observation, that's probability 0, right? So you take densities up and down, or you just take Radon-Nikodym of the numerator with the denominator, and you say, okay, that's Bayes rule for uncountable spaces. But what you lose is you lose the denominator of Bayes rule, then becomes a quantity that depends on the reference measure. So it's always very tempting with the standard Bayes rule to say, oh, I'm going to look at the marginal likelihoods, or I'm going to look at the denominator, and I'm going to try to assess if my observation was from my model or not. But maybe you get 10 power 4 kilometer per second, right? I mean, it can be anything. It's because it has a unit. But this is unitless. This is value between 0 and 1. Just tells you if your observation was sort of within the model or not. Very simple. And there's no integral. It's very easy to compute this. Or if you want to compute it even for a complicated model, it's just an optimization problem. OK. I hope this starts to be a bit interesting. So now, I mean, say, OK, let's try the Kalman filter, right? That's natural. So that's work I did with Adrian when I was visiting him in Australia last year. So just sort of plugged in, say, OK, we have our Gaussian possibility functions. So we really do the usual stuff. And actually, as a result, you get exactly the same mean and the same variance as the Kalman filter. Whether you write with probabilities or with possibility functions, the Kalman filter is the Kalman filter. And so that's really interesting because it means with all the calculations in the Kalman filter, actually they don't depend on whether you have an integral or supremum. You have the same quantities. And it also makes sense with I think Nia was talking about it yesterday. You can look at the sort of Kalman filter from an optimization viewpoint, and that's exactly what it's saying. You're just minimizing the distance, but I think it's a nice connection. You can, whether you do it with probabilities or with possibilities, you get the same result by a different interpretation of it. And so as I was saying, so the marginal likelihood is a bit different, and you can just evaluate it. It's just number of between 0 and 1, and it's quite useful in multi-target tracking because we always need to evaluate if the observations are likely or not with respect to our targets, right? So just one quick example, going to go fast on this one. So actually, when I was in Melbourne, my bike was stolen. I thought about doing this scenario. So we have someone, so there's the bike, let's say the bike was there, and we have a CCTV recording. We know at what time the bike was stolen, but we can't identify the guy on the CCTV recording. And okay, we have a suspect. We just assume we have a suspect, and the guy has been seen around downtown Melbourne at some times prior to the bike theft. And so the guy has some he has an alibi. He says, "Oh no, it can't be me. I was here at the tram stop between Latrobe and Elizabeth." And we have the second piece of information is the CCTV recording, right? But we have, as I was saying, we have some witnesses, but of course they can't remember exactly when they saw that guy, right? They don't like live with their clock. So they say, "Oh yeah, I've seen him on that street around that time, 2 or 7 p.m. for instance," or another type of information here is more like velocity related. You say, "Oh, he turned there in this sort of 10-minute interval," or "I've just seen him around that building," right? And so all this, I mean, of course you can fit random variables on this. This example is like nothing you cannot do with random variables, but okay, it feels like maybe it's not exactly the right modeling for these sort of things. And so here we've quite easily modeled the spatial uncertainty and the time uncertainty. We put everything together. And so at the beginning, we don't know what the guys is. Then we just run this thing. So I'm not going to go into the details of the implementation. So it's been seen on this street, but because we don't know the exact time, of course, depending on when he was seen, then he had time to walk down the other streets or not, right? Then here it's been seen around that building, etc. And at the end, we see, oh, it's possible that he was there, but it's not possible he was here. So I felt better about my bike. We found the suspect finally, or found the culprit. And even if you can do everything with random variables, it's interesting, I think, that if you want to, for instance, evaluate the probability that is around that tram stop, or it was really precisely around that point, if you just take those two subsets and evaluate the probability, of course, the probability of being there is a lot smaller because the subset is a lot smaller. So you say, okay, maybe I'm going to make my subset the same size, but then you have, because the street is so narrow, you have to take almost the whole street. So in this case, if you want to try to evaluate the credibility of the guy, is actually, you have to think a little bit. But with possibility functions here, we don't integrate, so it doesn't matter if this whole subset or if it's a single point. You say, is it possible to be here or not? And so there's no scaling issue here. You just very stupidly look at the supremum around this corner or the value at this point. So of course here it's particles, so you have to be a little bit more, at least you have the nearest particle. But in principle, you could just evaluate at this point and give you the possibility is there. And it's non-zero. Okay, so now I'll just quite quickly I'll go through the more interesting case where we have false alarms, the usual as I showed before. So again, here is not so obvious if I remove the state observations. Where are things, right? I mean, and well, you can do basically exactly what I did before. You can introduce a point process but uncertain, just saying well, we also don't know how many things are there, but that's maybe not random. And in practice, the number of objects that might not be random at all. So I have to change a little bit the definition of first moment. I put it between quotes because it actually makes less sense in that case. But here, and sort of unsurprisingly, I use my maximum, and I use the first definition of the expectation. Actually, this guy also, this has very nice properties. So here I just take it, I can deduce the possibility function. But instead of having, instead of having a sum, have a maximum. Makes sense? I was working with, everything was integrated before, and now everything is maximum or supremum. So here is a maximum. And actually, so I say, okay, forget about this. I don't have time, but to explain. But I'm saying I know absolutely nothing about false alarm. You can have any distribution or no distribution at all. It can have any number, any position. It can be completely correlated in time or not. Doesn't matter. I know nothing. I only know a lower bound on the probability of detection. So basically, what I'm saying is, I'm not saying, oh, I know that I see my objects 90% of the time. I just say, basically, I want to track everything that I see at least 90% of the time, or at least 10% of the time. The rest are not even trying. Same thing for probability of survival. And actually, that works pretty well. So it's a bit, so basically the target, this is some measure of error, but high is bad and low is good. I mean, it's the only thing you need to know. The target appears at time step 3. So here both, if I use a probabilistic Bayes method or possibility, both, of course, make a big error because you need time to understand that something appeared. Here, they're actually pretty equivalent. So when the target disappears, time, I think, 23, the sort of possibilistic version is a bit more opportunistic. Maybe it's saying, oh, maybe it's still there, so the error is a bit higher, while the probability comes back or the error reduced a bit faster. But this guy has no idea about the false alarm, right? So that's he has almost no information except how the target behaves. And the way I see this is basically is working by elimination. I don't need to tell him. I don't need to tell him what's the distribution of the false alarm. Like as human beings, we look at this. We're not trying to estimate the false alarm. We just know that maybe this thing goes in straight line, or we know something about the dynamic, and we just cancel out everything that doesn't behave this way, right? That's what we do. We do by eye. We do no estimation. We just look for patterns. And in this sense, this is what we're doing here. We don't need to know we don't need to know anything about the false alarms. We just need to know what we're looking for. We need to know how it behaves. It makes sense. That should be sufficient. And so just in a minute, it's quite nice, I find, to see that we can basically derive the first moment recursion is exactly the same form, but you replace sums and integrals by maximum and supremums. This, I can use the derivation by Pierre Dalmoral and do the same, have the same sort of idea. Here, there's no Poisson assumption. Actually, it works a bit differently here, and there's no there's no approximation here. We can just propagate our first moment this way. Maybe it's not going to be very informative. If our model is very bad, is going to say, well, the target could be anywhere, or there could be any number of targets. I have no idea. But that's what you get if you know nothing and if you don't give a proper modeling. But it's able to tell you, if your modeling is good, it's going to tell you that you know something, right? Okay, it's just basic stuff. References. Yeah, I don't think there's anything particular here. Thank you.
Any questions?
Yeah, so it's very nice that your method is so well as recursion.
I agree.
Is it stable?
This is quite recent. I'm still at the stage of basically implementing it. So, but this is I submitted. No, this is not even submitted. It's on archive. But yeah, I just wanted to show that the fact that the recursion exists, I think, is one step. I mean, overall, also clearly, there's a need to develop tools to understand what's going on. I mean, I agree with this. Of course, at the moment, I like a lot of the sort of guarantees we have with standard stuff. But I think if I was spending a lot of time on the guarantees without showing what it can do, why it's useful, then I might be wasting my time. So for me, it's important to check that I can actually do something complicated and solve a complicated problem and still be able to say that maybe you don't know everything, etc. For instance, so at least it's always hard to say better because it doesn't have the same information at all. This compared to the other one, this one has you can give it very little information. It's still going to work. So that's where the better is a very sort of qualitative here. So maybe you lose, maybe not as accurate. But for instance, in terms of uncertainty quantification, again, if you assume Bayes rule makes sense for these things. Then here you've not made any modeling assumptions that you don't know, or you just for the sake of writing things. If you don't know something, you can write it as such. And so, yes, in terms of uncertainty quantification, you're more likely to have something meaningful. Matt?
I think we should start between randomness and uncertainty, and that's kind of core to what I'm trying to do. But to me, I would find it hard to come up with an explicit definition of randomness which didn't involve uncertainty or vice. As in, to me, randomness is just saying you're uncertain about the value of something.
Yeah, but for instance, the inability to the fact that we have to use improper priors, for instance, is telling you that actually randomness is not good. Is not just uncertainty, right? It's because if you cannot have uniform uncertainty over unbounded space, because in terms of randomness, it doesn't make sense. You cannot appear at random anywhere in infinite space, but you might know nothing about that space, right? So that's why, for instance, if you have a discrete finite set, yes, I would say the difference would be very subtle. But as soon as you have uncountable, as I was saying, for instance, with the issues with improper priors, I think that's a symptom of actually randomness, not exactly uncertainty, right? You can try to model uncertainty with randomness, but you're going to hit a few problems.
I'm not saying it's not a problem, but it's more that I don't understand what the definition of randomness is. As in random, what does it mean to be random in that sense?
So I think that's a very important question. And so either you see it from like sort of pragmatic viewpoint, and you say either it's modeling. But I think to take the sort of frequentist idea that if you want to model something at random, that it should at least be sort of repeatable, and you should see some patterns when you repeat it. These sort of ideas, right? But that's a difficult part. I agree, and I think I'm not sure it's possible to define very precisely what you mean, right? So, but yeah, something can be argued. But a lot of people have spent a lot of time arguing about those things, and but I think because no one showed that the difference actually matters for practical problems, then it just remains a philosophical discussion, right? But now we have this, and we're like, oh yes, so what is the difference? When I'm supposed to use one or the other? And I think there's a lot of interesting questions there. But yeah, I don't have the answer to everything.
Yeah, continue on with the theme here. I don't quite understand why you object to modeling something that's not random but unknown using probability. I mean, in Bayesian Inference, there's lots of ways to justify probability, like
Sure.
Symmetries in beliefs, willingness to bet, extensions of the laws of logic, and so on.
Sure.
Those ways of looking at probability, they don't require randomness in a physical sense.
Yes, so I agree that there's I mean, in many cases, and I mean, clearly, probabilistic modeling has been very, very useful for a lot of things, right? And I don't even suggest to sort of replace, but I think in some particular cases, I think it's useful to have an alternative, and that's also why. So at the beginning, actually, I'm not going to go back. At the beginning, I introduced with the probability and then uncertainty on the parameter, and I think that's the sort of form that's really going to be useful. There's something you know well enough that you can put a probability on it, and it makes sense. But there's some other things, sometimes parameters, maybe sometimes something else that you don't know well enough. And I think for instance, in the multi-target tracking case, I mean, for the false alarm, the way you model the false alarm, I mean, you take Poisson for the number, but it's very constraining, right? And you might not know at all any upper bound how many false alarms you might receive. And so yes, you can put a parameter, but I like the idea of saying, well, we just really don't know. But yes,
there is a long history of course, of trying to modify the laws of probability.
Yes.
To sort of handle imprecise probabilities and things like this. Is your suggestion related to any of those things, like belief functions?
There are some relations. Actually, the people who do belief functions, for instance, they knew they're related to outer measures. But the way they write it, I mean, in my experience, actually, it makes it very hard to solve complicated problems. So, and all the publications I've seen, some people also the possibility, I mean, functions with supremum 1, as other people have looked at it, I'm not saying I'm introduced it, but they've only solved simple problems, I think, because their tools tend to make things extremely complicated, and they can't really address more complicated problems and show that there's actually a point. And that's sort of this part that I was trying to bridge.
Is there any sense in which you can think of what you have done as an approximation to the proper sort of probabilistic analysis?
So I think seeing the outer measure as an upper bound is nice, because you can say, okay, maybe, for instance, I have a family of distributions, but I don't want to spend time representing all this. I just take an upper bound for everything. So I think that's nice, and it helps intuitively to also understand things. But so yeah, as I was saying, in base rule, it doesn't propagate, right? Because you would need a minimizer at the lower bound in the denominator to sort of propagate this idea that it would be an upper bound. So I think it's important that there's such an upper bound, and it helps intuitively. But unfortunately, I would say it's not always true that we are upper bounding some family of functions that probability distributions that we would like to know. So, but it is related for sure.
Small one. So going back to the linear Gaussian case,
Yep.
I think from memory you were saying that your marginal likelihood is different.
Yep.
From the standard stuff. Would that mean that if I were to do some sort of parameter estimation based on this marginal likelihood, I could get different results?
Yeah. Well, if everything's Gaussian, no. But if you
In the parameters, I mean.
yes, in the parameters, if it's non-Gaussian, yes, you might get a different answer. So it's it's something that's also.
Have you also looked at comparing models? How would you do this in the setup?
So it's a good point. It's something that's very sort of natural to think, and I mean it would work to compare models, but actually so probabilities do have some nice properties in that case that in a sense maybe are a bit restricted, but are still nice. And actually those. So for instance, when you compare models, it tends to depend on the size of your parameter space. So you sort of naturally you favor parameter spaces that are smaller, and so you favor simpler models to some extent. And so this we don't have it here because it's completely dimensionless, and it really doesn't depend on the size of the parameter space. So it's something I try quite hard, but at the moment I don't see where it could actually be useful for that. Thank you.